Okay, Unit 2A, Day 3, Properties of Related Lines. I'm going to draw these out the best that I can, and then we'll talk about what happens if these are coplanar or non-coplanar if possible. So if M is parallel to N, and N is parallel to K, then what can be determined, I'm putting these little extra arrows in here so that we can see our parallel markings. So if M is parallel to N and N is parallel to K, then M is going to be parallel to K. Is this always true? And if not, show a counterexample. So one of the things I'm going to try to draw out here to the side is kind of a side view. Okay, so if all of these lines are coplanar, then I have M, N, and K. What happens if I take one of those lines and move it off of the plane? Okay, so as of right now, all three of these lines are in the same plane. What happens if I take one of them, as I said, and maybe I put in here, and what if I put K up here? So our question is M still parallel to K? Well, if we look at M and N, those are parallel. If we look at K and N, those are going to be parallel. Remember, this is a side view, kind of like if you're holding a pencil pointing away from you in your face, okay? You're seeing like the erasers of these pencils. And K and M. So our question is, are these two still parallel? And our answer would be yes. This is still always true. So here is our coplanar example, and here is where all three are non-coplanar. Now, M and N would be in the same plane, K and N would be in the same plane, but M and K would create a different plane all of their own, unlike the first one where all three lie in the same plane. So if A is perpendicular to B, here are A and B, and B is perpendicular to C, then what do you think we notice as long as these are coplanar about A and C? A is parallel to C. Is this always true? So this is where things get a little bit weird, okay? We're going to have to imagine that one of these lines is located in a different plane. The easiest way to do that is to draw like the corner of a box, okay? So I'm going to start out here. And maybe this is A and B. Here's our little marking. And what happens, like I said, if this is the corner of a box, three-dimensional figure, here is line C, okay? So are A and C still going to be parallel? And that is a no, okay? So only if they are all coplanar. Okay, think of the corner of your room where all three of those lines meet. If if the intersection coming up from the floor is B and the two others are A and C, it's pretty easy to see that A and C that run along the ceiling are not parallel to each other. Okay, that's what we've got here. So we're going to talk about what we can assume and what we cannot assume. We can assume that all of these points that we see are coplanar. Angle something and BHD. So here is BHD. So that would be FHD. Are a linear pair, and BHD and FHG would be our vertical angles. A, H, J, and D are all collinear. Line AD and BF intersect at point H. And things that we cannot assume. We cannot assume that G, F, and E are collinear. Not unless a line is drawn for us. We cannot assume if BF and CE, if those two lines intersect. We cannot assume that BHA and CJA are congruent. And we cannot assume anything to be 90 unless we're told that something is perpendicular or that we have that little box there. So which of the following statements can and cannot be assumed? E, D, and C are collinear. Well, they're on the same line. They all appear on the same line that is drawn. So this is a yes. The intersections of lines BD and EC is at point D. Yes. And in these last two, we have two perpendiculars. Even though they look perpendicular in our diagram, there is no indication that anything is perpendicular. So both of those are a no. We're going to move into some properties that we're going to use in our proofs. And these first four, addition, subtraction, multiplication, and division, are all things that you have used before. So if A is equal to B, then A plus C is equal to B plus C. And same thing with subtraction and multiplication and division, as long as C does not equal 0 in division. Our next three are our reflexive, symmetric, and transitive properties. So for reflexive property, A is equal to A. This angle is the same as itself. Okay? Notice our variable does not change. A is equal to A. Our symmetric property, if A is equal to B, then I can flip those around and B is equal to A. And for our transitive property, if A is equal to B and B is equal to C, then A is equal to C. For our substitution property, we will only be able to use substitution for equality, so just kind of keep that in mind. If A is equal to B, then B can replace A in any expression. So these three here that are highlighted, these are all our properties of equality. And the reason that I highlight those three is because here in just a second we're going to show them with properties of congruence. And it's the same thing. So we have reflexive property of congruence, symmetric, and transitive property of congruence. Our reflexive is one piece, is the same as itself. Symmetric are two pieces that are the same forwards and backwards. And then transitive is where if A is equal to B and B is equal to C, then the two on the ends are also equal to each other. That works for our congruence properties as well. When it comes time to name these in our actual proofs, the reflexive property of equality is going to be different than the reflexive property of congruence, so it's going to be important that we either put the equal sign or the congruence sign after them. Okay. Another thing that you will see is that substitution looks a whole lot like transitive, but substitution is only with numerical values. Remember, it's only with those equal signs. Think of substitutions in algebra. The only thing that we can substitute are things with an equal sign. So, a proof is a logical argument that shows that a statement is true. And a theorem, unlike a postulate, is a statement that must be proven to be true. In our theorems, we're going to have lots of if-then statements. Okay, so name the property illustrated in the statement. If R is congruent to T and angle T is congruent to angle P, then angle R is congruent to angle P. There are three pieces here. This is our transitive property. And it is our transitive property of congruence. And if NK is congruent to BD, then BD is congruent to NK. There are two pieces here. This is our symmetric property of congruence. Now, these next few, we're going to start out super easy with some algebraic proofs. You have done this. Anytime that your math teacher has asked you to solve an algebra problem and explain the steps out to the side, that is an algebraic proof, okay? So our proofs are always going to start out with our given statement. And our question is, how are we getting from A to B? And that is the reason that we write on B. So if we look from A to B, we notice the difference here is that 2. And because we are multiplying by 2 on both sides, our key there is on both sides, this is just our plain old multiplication property. And there's only one, but if you want to, you're welcome to put the equality symbol after it just so you kind of get in the habit of doing that. Okay, so the next thing that we do, notice that those 2's are gone because we have multiplied them, but this isn't our multiplication property, it's something more specific. Whenever I multiply this 2 times everything on the inside, this is now our distributive property. Now, multiplication is the act of putting those 2's there, and then distribution is the act of actually doing the multiplication on both sides. So follow what it's doing here, because I know there are a couple of different things that you could do. But in this case, to move from C to D, we are subtracting that 3. So it's our subtraction property of equality. And then, to solve this further, we are dividing property of equality, our division. All right, so remember that these lists are up here. You're always welcome to come back and look at these as a review. So we've got, let's see, 2 more proofs for today. Our first is always going to be our given. Notice that it is right here. And now we're just going to follow the math. So again, the worker here is wanting us to get rid of our fractions. So you'll notice that we're multiplying by 2 on both sides. So this is our multiplication. And you can put the equal sign after it just to get in the habit, but it's not going to be counted wrong if you don't. To distribute, that's what it wants us to do next. So it wants us to multiply those 2's into the parentheses. So 2 times 4 is 2. 2 times 1/2 is going to be 1. 2 times 7 over 2 is 7 minus 2x. And pay close attention here to our next step. Let's see. Oh, that should be an 8. That's my bad. Okay, I was like, where's that 1 coming from? Okay, 2 times 4 is 8. That's not division. All right, so the next thing it's doing is subtracting this 7. And it wants us to add next. So it looks like if we move from here down to here, it wants us to add the x to both sides. So it's going to be 1 is equal to a negative x. And by flip-flopping the negative, you can either put multiplication or division because both of those will allow us through multiplying by -1 or dividing by -1. So I'm going to write down multiplication. And then notice we are flip-flopping the pieces of the sides, and these are not the same thing. So this is not the reflexive property. This is our symmetric property. We have 2 different pieces, and we are flip-flopping them. And our last one. So we have ray BD bisects angle ABC. Now, the first thing that I like to do is go ahead and mark this up. So if I know that ray BD bisects angle ABC, I'm going to go ahead and mark those 2. And this is our given. We want to prove that the measure of angle ABC is the same thing as 2 times the measure of angle 1. So I want you to think about this for just a second. If these 2 are the same angle and the same measure, isn't it reasonable to think that we could replace this 2 with another 1 and then have 2 angle 1's to add together? That's the thought process that we're now going to put into our proof. So here we go. We have our given, and because of our definition of an angle bisector, I could mark those 2 angles congruent. So I can say that angle 1 is congruent to angle 2. Those are those markings that I put in there at the very beginning. Now, bisecting tells us that our angles are congruent, but in order to work the math with these angles, I need them to be equal. But if they're equal, they're congruent, right? So that's the next step that I'm going to take. I'm just going to change the way that they look. The measure of angle 1 equals the measure of angle 2. Now I'm saying not only are they congruent, but their numerical values are the same too. All right, so the measure of angle 1 plus the measure of angle 2 equals the measure of the whole thing. If I am taking 2 smaller angles and adding them to be the total angle, we're doing exactly what we see over here. This is angle addition. This is angle addition, not regular addition, because remember that regular addition property of equality is whenever we add the same thing to both sides. Now, this proof does have a mistake in it, so I'm going to mark it out now. This little 2 down here should be a 1. And the reason that I can swap those out is because if they are equal, as I've said up here in step 3, then I can replace one for the other. So through substitution, I am going to take this measure of angle 2 and swap it for the measure of angle 1. Now, our goal here is to have the measure of angle ABC equal to 2 times the measure of angle 1. Now, this says distributive property. I will take that, but I almost see it as like an undistributive property. So two things that would probably be better is combine like terms. You hear that all the time in algebra, right? Combine like terms, combine your x's, combine your numbers. Or you could just say simplify. Okay. Now, another thing that you will see, and I'm not going to be super picky in this case with it, technically this should start with 2 times the measure of angle 1 is equal to the measure, oh, sorry, I put my M in the wrong spot, the measure of angle ABC, just because of the way that the order is in. And then we'd use the symmetric to flip-flop it, but I'm not too concerned about using the symmetric to flip-flop that. This is a very basic intro to proofs. The ones that you're going to have on your homework are mainly going to be the algebraic proofs. So remember, your question is, how did I get from the step above? That is what I put on this line right here. When you come to class, we'll have the opportunity to look through some of these, but please make sure that you've watched the notes and give some of the homework a little bit of a try, and then we will look through them. I'm going to save this one right here as kind of a warm-up for the beginning of day 4.